Hi, everybody. So the presentation I'm going to give here is actually two presentations I have had to put together. So there would be something about controlling folds with implicit modeling approach, so what Laurent already introduced a bit, and also another tool which is the rigid element method to model structural things. So I still try to make it a bit consistent and try to introduce all that all together. Just considering the different approach we can have to modeling geology. So I would say there is the modeler or geomodelers approach, which is actually data-driven. So you have generally quite a lot of data, and you want to interpolate or to make something out of this data. So all the reasoning is mainly based in the current state of the geological structures, and you take data and derive your model. So it's good because it gives you quantitative model you can use to quantify things. Now there is, on the other side, something which is more geologist approach, which is reasoning through time. So putting a geological scenario and some tectonic, some history aspects on top of that, considering multiple phases, and building a little model in his mind. So, for example, what you could do in Nodi, so that's more of an expert-driven approach, and it gives you a qualitative model as opposed to the other method. So, in fact, both approaches are very good because they allow you, on one side, to take the whole historical knowledge, geological knowledge into account, and on the other side, the data. But they are not really matching very well together, so I think we need to reconcile a bit more of these two approaches. So I'm not saying I've done that, but just a few tools to help to go toward there. So in the first part of the talk, I'm going to present you Read, which is a tool I think we can use to represent the deformation events à la Nodi. And in the second part, something to better integrate structural data in folding. So first of all, Read, which is basically explained there. So we have an initial model we want to deform and edit interactively with a limited number of structural parameters. So coming back to what we would use deformation algorithm for in geoscience, first application would be editing. You start with a model you spent months to build, and you want to see what if I change or something. So you won't rebuild the whole model, but you could try to edit it to change it a bit. So for example, moving this layer by changing the amount of displacement along this fold. So you can play with that. You need deformation algorithm to do that. You could use deformation algorithm to completely forward model your model. So you start with a flat structure, for example, and model deformations, all that, to rebuild the history, in fact. And last, there is the restoration. You can start again with your model you have spent a lot to produce and test if you flatten it again, how it behaves and what it tells you on the structures. So the specification of these tools would be to be physically consistent, so it has to look like natural deformations. Interactive, because we want to play a lot with that, so it has to go fast. And the scale has to be adapted to what we try to deform, so not too fine, but not too coarse too. We don't want to lose too much. And it has to be robust and parsimonious, because we don't want to invert things then for thousands of parameters. And actually, the tool I'm presenting here is considering maybe the specification we should have is putting this really, really far down behind all the others. Why? It's because, why can't we do that? We would like to rely more on the geologist's interpretation than on the data and try to see what we get. So it means allow it to be a bit more interactive. So what we want is getting rid of meshing problems and is the automation of the process by increasing the interactivity and robustness. So it's not really lowering that, but as soon as it is increasing this, it's OK. And in the end, when you think about it, generally, you don't have enough information to run precise simulation of how the rocks behave, at least at this scale, at the moment of the when you build a very early model. So we try to look not into geoscience, but in computer graphics, in fact. It's a world of deformation tools. And they have quite interesting physically based deformation models. So for example, the one we are using here is considering a shape. It is embedded in little cubes here. Some parts are fixed and some parts move. And it allows you to bend it. So when we saw that, we thought, maybe that's a good idea to apply a tool to apply to geoscience to make folding. The way it is done here, so we have layers, which are surface, any type of element here. This element is, so it's embedded in little cubes here. And this one is fixed. This one is going to move toward this X position. It is free to move in Y here. And it progressively deforms to go there and produce you a fold like that. So how does it work? There are four main steps. So you start with an undeformed model. You can see here that there may be quite a lot of little details here. And I was speaking about the scale of the deformation. And we want to keep this little model, these little details, but we don't want to pay the price of computing their behavior very precisely, because we know the overall deformation will apply is a general fold here. So we encapsulate this in larger scale elements, which are rigid elements. We put some boundary conditions. So this one spin, this one is blocked, this one translates. Okay? And we get little deformations like that by trying to minimize the cost function. I will explain later what it does. And then you just have to apply the displacement interpolation when you find it is good enough to your initial geometry. So you only pay the price for details in the end. The cost function is very important here. It's trying to minimize the difference of displacement between the elements. So it's very close to minimizing the mechanical deformation, mechanical energy, in fact, of the deformation. So if you consider two neighbors elements and a given point of the volume here, you could trace the displacement of this point according to this element. You could look at the displacement it would have following this element too, and look at the difference between these two final positions. This distance gives you, in fact, a kind of matrix of the difference of displacement between these two elements applied to this point. Then if you integrate that over the volume, you have a metric of the difference of displacement. So that's basically what is done with this tool. Then in the end, if you have an object here, and it is embedded in little cubes here, we can compute the displacement, the final displacement of each node by locating here within the cubes, looking at the displacement of this red dot after each of the elements, okay, and linearly interpolating between them, or using more better interpolator if you want, but linear is generally quite enough to have good results. So now a bit of geology, because that's what we want to do mainly with this tool. We try to recreate, for example, here create a synthetic model with different deformation events. So we started with already quite complicated stratigraphy that we embedded in a deformation tool. Here, just a layer. This part is fixed, these two, and we just push this little cube here, and it produces complicated fold. Okay. Then we add another stratigraphic layer on top of that, and again, apply a deformation event. So the idea we had with Laurent when I came to Monash was try to control all these little constraints here in yellow to make it a fold parameter oriented tool. So, for example, here, specifying the shortening of in that direction, the location of the fold, the axial surfaces of the fold, and the amplitude of the deformation. So it's not really done yet because you have to put all that manually, but we know that it's possible to do do it with this tool. That's an example. And the geometry you get in the end can be actually quite complex out of very few parameters, so structural parameters at the beginning. So the pros is it's fulfilling the constraints, the specification we put at the beginning. Now some things were missing. For example, faults. So we looked at what exists for the faults in computer graphics, and here it's a bit deceiving because what they are doing mainly is considering breaking objects, and faults are not behaving like that. So what we proposed here is to take an implicit definition of the fault. So it's using the distance field, because actually we need to locate how far we are, given one point, how far we are from the fault and in which direction it is. So we'll try to minimize a cost function based on that. So if you consider an initial square here, you know the distance to the fault. After a certain number of iterations of the deformation, you can also estimate how far you are and which is the direction. And you can try to optimize the next position to minimize this gap of distance. So try to continue to be at the same distance of the fault. Which is good is that it's an iterative process and you can try to linearize at least each step this. So basically in a few iterations here you take this element toward there and there is a fault here. So all these elements are cut by the fault. The first iteration, it is going quite far of the fault, but it is trying to recover then in the next iterations. And so it has simulated the sliding along this fault quite well. So you can let it run and displace progressively things. So with this tool, we hope we could do some model editing quite fast, and even when there are faults in there. The main point being, it is adapted to the scale of the deformation and not to the detail of what you want to deform. I think that's the most important point. Now I will move to implicit modeling of faults and try to put some new constraints into that to actually represent the faults. So the problem of putting these faults into implicit modeling is that first, there is a time to take into account, and we are only modeling, remember, in the modeler's approach in the current time. And it's actually quite complicated to consider that multiple events occurred and they interact with each other, and you have to take into account the previous event when it happened. And also, so the current geometry is the result of complex multi-event geometry. Then the second aspect is data we are considering, or measurement. So first group of data is stratigraphy location. So for example, looking at some contacts, the position of a contact, in fact, stratigraphy I was meaning, it's already good information to know that you have a continuous progression of layer through the space. If you have some discontinuity, you will have to take that into account too. And so there is also the orientation of the different contacts when you can observe it. But we have actually far more. That's what Laurent was presenting. So we know how to. We observe hinges, limbs, axial surfaces, the fold axis. We can observe vergence in some place, and we have some information or idea about what type of fold are possible. So the overall shape it has to show, the cylindricity, all that, and actually most of the geomodelling package, I think generally stop here because these constraints are not fully taken into account. There are some things about axial surfaces and fold axis, but it's probably not enough yet. So what we are trying to add here is all these constraints. So how does implicit modeling works? And here I'm explaining first in a very general sense, and then I will zoom into one of the implicit methods I'm using in particular. So the idea is to have this stratigraphy, first observation, and we want to reproduce it in the space by using some data, some control points, and regularization term to say how it evolves between the control points. So the observation, there are stratigraphic values we can see at some points if we know this information. The orientation of the bedding too. Okay. And the regularization term would be to have continuous values first and try to make the gradient vary smoothly or try to respect the way, in general, the data vary in the space. So, for example, you can use geostatistical analysis to try to constrain the way it varies in space. And then you use that to interpolate in 3D the scalar field. And if you want to take a particular surface, it's an ISO value of this scalar field, for example, here, the yellow one. Now I'm going to talk about the discrete implicit modeling. I say discrete because I don't want to speak about packages here or software. So it's mainly what is done with GoCAD, SCUA, or Structural Lab. And there is a big difference between this approach and the others approach, which is because we consider a discretized region of interest and the mesh, which is acting as a support of the computation. So there is a region we want to compute in, and a mesh generally with simplexes, so triangles in 2D or tetrahedrons in 3D. And in fact, the stratigraphy, so the scalar field, will be represented as a piecewise linear field on this object. So in each little triangles here, you can determine the value at a given position by the value of the three corners of the triangle here, and it is linearly evolving linearly in this element. So it means the gradient of the scalar field is constant over one element. Okay, so that's what is expressed here. Your scalar field is a linear combination of all the values, and the gradient in there is constant. It's just a matrix multiplied by the value of the corners. Okay. So with that, we can implement the constraints, so all the observation, and build a big system of linear equations. So simply using these equations and deriving some linear equations. I don't want to go too much into details here. And when you solve this system, you get the value at each corner that honors the constraints. So you get the whole scalar field to represent the stratigraphy. The problem is that one of the constraints is to try to smooth everything, so try to make the gradient as constant as possible. And in fact, it is first limiting the fold, because if you say the gradient doesn't change when you move away, it means it is just flat. And it kind of allows to have a variation, but it will promote, in fact, parallel folding, because it won't try to have the thickness of the layer conserved through the fold, which is not the most general case of folding, I think. So how the geological structures in general are taken into account in there. I would just consider the folds first, because I think they are quite well understood and put into these packages. So the folds, they are described with structural parameters. We know the location of the fold generally, so I just say the center here. The orientation, azimuth and dip. The slip the fold may have. So you try to characterize your folds with structural parameters. And then you alter the mesh or the interpolator or whatever you want by knowing this geometry and these structural parameters. And it works quite well. For the fold, there have been very few attempts, in fact, to describe the fold in terms of structural parameters and try to control the interpolator with that. Generally, you get the fold by having two different measurements, and then it is smoothed. So in the end, you get a general idea of a fold, but you never control if there was a fold there. You never describe it in geological or structural terms. So what we propose to do is define the folding by additional field and additional information. So we would represent the foliation field, which is relatively concordant with the axial surface field. Okay? And so it's good because the foliation field is easier to measure. We can make observation in the limbs, so we don't have to actually see the hinges to understand there is a fold. And this field, at least the latest event, is relatively consistent over the area. It should be nearly straight across the whole area. And we use also the concept of vergence to quantify how much it is folded. So this vergence, so turning the latest foliation towards the one which is deformed, so this tells you, in fact, where the folding occurs and how intense it is. So we use a quantitative version of the vergence, so namely the angle, in fact, between the two here. Okay? And also, so the fold axis, but I won't go too far with this one. I'll show just another picture in the end. So the process we propose, there are two things, in fact, here. We are the overall process, which is going to model one folding event after the other, trying to constrain one by the other, and the different constraints we have implemented. So the process would be to interpolate S1 here, then analyze the vergence in the observation we can have to try to understand where the fold is locating, how it is, what is the wavelength, so to derive a fold intensity. Then we can just, in every part of the space, know the fold intensity after the value of S1 we have. Okay? And based on that, we would take this orientation, so the x direction of the fold and z direction of the fold, and rotate them into the space based on the fold intensity to derive the gradient of the stratigraphy we should have. So in every space, every point of the space, we can try to estimate the rotation of the gradient if there is a fold with these parameters. And then we just have to interpolate S0. Okay. Which is good is that we can control the different parameters we can put in that. So for example, the position of the fold center. So it's around there here, and I just move up or down the position of the fold. Okay. You will remark that it is still relatively honoring the two control points that are here. Okay. You can change the interlimb angle. We can change the orientation of the axial surface, the wavelength of the fold, the tightness of the fold. So any parameter you can use to control the folding, in fact, you can change it. And it's giving you a whole world of different possible models with just one fold here, whereas classical approach would only consider this model, which is not even looking like the same kind of fold that here. So a lot more parallel style. The very important thing is the constant gradient constraint, so the regularization term we would use. It would generally promote, so constant gradient promote parallel fold, so it's not really good unless you really want to have parallel fold. So for similar folds, you don't want the thickness, in fact, of your layer to be constant because it varies. It is increased in the hinge. So what is conserved is the thickness in this particular direction, so in the x direction of the fold. So we have implemented two constraints. First, a conservation of this length. So it is projecting in each tetra the gradient of the scalar field onto this direction, knowing that the direction, if the fold is a bit bent, for example, could change from a tetra to another. Okay. We compare this measurement between the neighbors and try to erase it. Okay, so that's the first way to do it. Another one, which is a bit stronger and assuming a bit more, is to say, just considering one tetra, if we don't have a lot of information about the thickness of the layer we want to represent, and that would be important for something else just after, we can just say we want this value to be a certain amount and the same everywhere. And this is, I'm going to show some result now to show how it is working. So first, we can try to actually simulate fold with that and not just interpolate and smooth thing. So at a recent conference, I've seen a little drawing like that with fold on two sides, and there is a gap of data here in between. And Mark was interestingly pointing out that interpolator will just smooth what is in between and completely miss the fact that you have a fold like that, unless you go and draw the fold by hand. So it's basically nearly what we are drawing, but just doing it in a more automated and systematic way and using implicit fields too. So with our constraints, it is in fact reproducing quite well this wavelength and propagating it through the model. So what we need to do is in fact to infer the fold parameters from data, okay, and then to try to optimize this parameter to fit data and try to represent whatever is in between. But there is not only one solution. Here it's just the most likely, I would say. What else can we do with that? We could play doing some simulation to do some uncertainty study then. So for example, if you consider the different model you can make by changing the data by a certain amount, you get some variations of the model here. But we could do the same using the structural parameters, so changing what the type of fold could be. And you actually change, not changing the data, you get a series of models that kind of honor your data still, because it is still quite close of what you see, the orientation you see at the data point, because it is still interpolating between those data. But you control the parameters you put for the folding, and you can then derive which folding is possible, likely or not. What else can we do? We could do interference pattern, in fact, because everything we define here, the constraints are defined relatively to implicit, so to scalar fields. So it's really easy to deform the scalar field, and then the constraint is also taking this deformation into account. So the strategy is we model the earliest fold first, and then we go backward in time. So for example, here I have two orientation, so two data points here, and we consider F2 generation fold in that direction. So the parameters have already been chosen, and what we see here, the scalar field, is in fact the S1 deformed by S2. And the coloring corresponds to the fold intensity we'll put for the next event. And then we can apply the same constraint using this surface as an axial surface, and you get a foliation field, S0 field, which is deformed and taking into account both deformation events. Okay, so you have S2, F2, F1, and S0 here. Another example with tighter folds, just I try to push the model as far as possible. Of course, when you get things that are really tight and really deformed, at some point you start to lose the continuity between things, and it's getting more difficult for the interpolator to actually interpolate. Okay. Just another picture to show that this is not only a 2D thing. All the pictures I've made are in 2D because first the program in 3D was not working very well. That was all of these pictures have been done with Mathematica, so it's not really computer intensive. And but all the formulation is actually in 3D. And here I've put this example where you have the axial, so you have a fold like that, with an axial a fold axis which is not straight, so it's not cylindrical, it's double plunging fold. And so simply instead of rotating the orientation perpendicular to the screen here, you do it around the fold axis, and it's exactly the same constraint. And it's working quite well too. So just to conclude, I would sum up the contributions I've presented. So some tools to model 3D folded geometry. And to do that by trying to take as much advantage of the complete structural observation we made, so including all the structural observation, including folds and foliation fields, versions, all that. And what I would call, I'm not sure it's really English, but time-aware approaches. So we want to have methods that are represented current geometry, but if they don't honor the fact that you have had several events interacting with each other, then your model is just wrong. Of course, all the models are wrong. That's the base. But this one is just not realistic at all. So you still want to produce things that could tell you something about what you can find in the subsurface. So RID can be a tool to do that, and implicit folding also. I hope I've convinced you it's an interesting tool to look here for. And yeah, all these things, RID for the folds and the implicit folding is trying to take full advantage of the implicit approaches. So that would be all. Thank you for your attention, and I will welcome questions, of course.